I will quickly go over what a spacecraft is made out of, or its composition. So very quickly, I like to think about spacecraft as robots, and robots as likelihood or likened to humans. So here I have a comparison of humans and spacecraft components. So a spacecraft brain is called the Command and Data Handling Onboard Computer. It's the main processor that computes data products and sends out commands. The critical thinking that we operate with is like the command and data handling flight software. It encodes telemetry, which is just another way of saying data, and commands and processes data. Our digestive system can be likened to power energy generation, which could be solved with solar panels or radioisotope thermal generators. Our eyes, ears, and nerves are like sensors on a spacecraft. This could include a star tracker, sun sensor, gyroscope, magnetometer, GPS. The commonality lies in that we use external reference markers to resolve attitude, which is pointing and orientation, and angular rate. Our mouth is like a spacecraft's communication system. You can have a radio which transmits signals. And then our skeletons, ligaments, and skin is like a spacecraft structure. It supports loads, contains all components, it keeps all of our stuff together, and it also keeps some external geometry. Our metabolism, in fact, is like the thermal subsystem in a spacecraft. It warms or cools components within operating range. Our fat is like a power storage system. Our blood is a power distribution system. Our nerves are like the command and data handling's harness system. So it's like the wiring that connects all of the daughter boards, or our hands and our different components on our bodies. Our arms, heels, and toes are like actuators, which are typically reaction wheels, thrusters, or control moment gyroscopes. They're what helps us pivot and move. Legs are like propulsion, where on a spacecraft, it offers translational displacement. Okay, so that wasn't so much a rigorous definition. That was more so an entry way of looking at spacecraft for those who are not familiar with spacecraft. Different segments of a space mission include the ground segment, the launch segment, and the spacecraft. So our class is going to focus just on the spacecraft, but I think it is good to be informed about the functions of the different segments, because you're going to have to design some of those details into your spacecraft. So how does the launch vehicle affect the way that the spacecraft needs to mount to the fairing? How does the ground station affect the way we build the communications on the spacecraft? So the loop, or the way that a mission goes, is that you need to maintain a launch facility and a ground station prior to launch. The launch vehicle gets you to space. The spacecraft does its thing in space. It hopefully does a lot of science or a lot of technology demonstration. The ground station then follows up with the spacecraft, talking back and forth about what the spacecraft has discovered and what it should do next. We're going to learn about these other segments, but only as it pertains to the spacecraft. Now, what does the spacecraft include? This is a breakdown of the spacecraft and the labeled subsystems. So a spacecraft consists of a payload, which we talked about rigorously today, and of a bus, which is the technological support for the payload. The spacecraft bus includes a structures and mechanisms subsystem, an attitude determination and control system, a communication and data handling system, an electrical power system, thermal control system, propulsion, communications, and sometimes, if you have human payloads, an environmental control and life support system. So I didn't talk about human spaceflight in today's payloads. I was just focusing on robotic missions, but this is important for human spaceflight. So to review, a spacecraft includes these different components where there's a hierarchy. A spacecraft integrates a payload and a bus, and then the bus, which is the technology that supports the payload, includes different subsystems like structures and mechanisms, attitude determination and control, communications, environmental control, which is relevant for manned or crewed space. Then there's electrical power systems, thermal control, propulsion, and communications. There are 8 potential subsystems in a spacecraft bus. In the Artemis kit, there are only 6 subsystems that you need to worry about. So in the Artemis CubeSat kit, we won't have a propulsion system and a environmental control and life system ECLSS. Your team will be responsible for balancing the payload and the bus design to fulfill your mission. I imagine a potential team breakdown could be one person to be the chief scientist and systems engineer, so managing the payload and the integration of the other subsystems. And then for each other of you, you can be experts for 2 of the subsystems while also being the subsystem engineer that interfaces with the chief systems engineer. All right, I want to go into detail about each of the subsystems to make sure that you understand the scope and responsibility of each subsystem. So for structure and mechanisms, for large spacecraft structures and mechanisms, or ordnance, which is not included typically, I don't want to say that. Ordnance is a special kind of mechanism. Ordnance comes from a military background where they are explosive devices. Ordnances are usually used for deployment if you need to separate yourself from the rocket, say. So structure and mechanisms includes all of that, the structure, which is the skeleton, the exoskeleton, the different frame and brackets inside. Mechanisms include maybe active components that swivel or rotate or translate. So mechanisms here, this is the soil moisture active passive or SMAP satellite that has this huge antenna boom that supports a large antenna. Yeah, the structure is here, that large boom, and the mechanisms could be the rotary arm joints or deployment mechanism for this antenna. The structure and mechanism subsystem provides structural support to the spacecraft components and spacecraft configuration. This particular mission had a unique large deployable antenna, and it's also rotating. So the structures lead, for example, would have to figure out how to go from a collapsed satellite to this deployed satellite and make sure to analyze the different stresses and strains that are imposed on this boom, on the antenna. For example, the antenna may have some kind of pointing resolution, and while it's swiveling, you want to make sure that the boom is stiff enough so that it retains its shape. The structure and mechanisms subsystem also provides mechanical support for moving spacecraft elements. So we were talking about how this large antenna swivels. So there could be a motor here that provides that swiveling or constant rotation. And then we talked about ordnance, which is the separation of components. The electrical power system supplies the spacecraft with power required to sustain bus and payload operations. For electrical power systems, the 3 main verbs you need to know are generate, manage, and store. So the electrical power system here says at least generate and distribute power. So that can be from like radioisotope thermal power generators, from solar panels, from fuel cells. The EPS system can also provide excess power that may be stored. So there's that verb stored. Different technologies for this could be batteries or mechanical flywheels. For most spacecraft that do not venture beyond the orbit of Mars, power generation is usually accomplished via solar cells. That is not to say that solar cells are not used past Mars. The farthest out satellite or orbiter that is using solar cells is the Juno spacecraft, which is orbiting around Jupiter. But granted, those solar panels are humongous. And I think that will be the limit in the near future, because beyond that, the mass and power trade study doesn't quite make sense. Okay, the command, telemetry, and data handling, or CDH system, receives, validates, decodes, and distributes commands to spacecraft systems. It gathers, processes, formats, and records spacecraft housekeeping, telemetry, which is data, and payload data for downlink and or use by the onboard computer, which we typically acronymize as OBC. All spacecraft must handle commands and data, even Sputnik that had to send ones and zeros across electronics to blink its light. So here is a basic layout and a systems diagram of basic command handling. On the left, this is more of the communication subsystem, but say that you have your antenna that receives a command, a spacecraft transponder is part of that communication system, and then everything to the right, the command decoder, the command logic, and then the commands to other satellite systems. That's the job of the CDH subsystem. The CDH subsystem includes not only hardware, but also the software. So it's like the brain and the thoughts. For communications, we just alluded to, people also say comms. The comms subsystem receives command data transmitted from ground or space-based communications. It also transmits telemetry data, which contains spacecraft health and payload data, to ground space-based receiving antennas. All spacecraft must communicate with its operators. Sputnik was a one-way communicator where it was just up there to blink its lights so that mission operators on ground knew that it had survived in space. For the very simple satellites and potentially for these CubeSats that we're going to build, it could be a one-way transmission where the satellite is just sending data and there may not be ability to command it from ground. I think that the Artemis CubeSat kit has that capability. Hopefully you'll prove that in your link budgets. But there are ways to simplify the mission if you just want to do a one-way transmission. The attitude, determination, control, and sensing subsystem, it kind of spells out all of the verbs right there. So I'll just define that attitude is your orientation or the spacecraft's orientation. Determination, maybe let's start out chronologically. The first thing the attitude, determination, control, and sensing, or ADCS subsystem has to do is sense. So the sensors, as a part of this subsystem, senses changes in the spacecraft orientation and stability. It uses the space environment references, so stars, sun, the Earth's limb, to figure out how it's pointed in space. Then the determination is if you have multiple sensor measurements, then can you determine a good estimate for your attitude? And then that final component is if you want to be pointing in a certain direction, you then control your spacecraft's orientation using things called actuators, which include reaction wheels, for example, or control moment gyroscopes, or a little attitude. I think it's called reaction control thrusters. Okay, this picture is a layout of the Kepler Space Telescope, which has these star trackers. It has reaction wheels. Yeah. Okay, the thermal monitoring and control subsystem maintains the satellite components within a required temperature limit by monitoring and heating or cooling components as required. Here's a picture of the ISS, and in the red circles are these radiators. It's actually shedding heat because the ISS gets quite warm. You would think that because space is cold, that spacecraft also feel cold, but because of the vacuum, that's quite insulating. So really, the ISS that has a ton of solar illumination actually builds up more heat. Okay, so questions about a spacecraft's composition that deserves answers. So I think I addressed this already about spacecraft beyond the orbit of Mars using RTGs. That is true. Are there any other power alternatives commonly used, or is it just these two? There are more details in the power chapter that I would love for you to dive deep in to investigate all the different power sources. But the short answer is yes, there are different power sources. I think for outer space, so past Jupiter, like I was saying, RTGs are the most promising and commonly used option. Both Voyagers have RTGs. But there are very creative solutions for LEO, and the Huygens probe was one of the probes, I think it was actually Japan's. Anyway, one of the probes, these landers, actually uses a fuel cell, which is, I'm sorry, I'm feeling scattered this morning. Not a fuel cell, a primary battery, which is it cannot be recharged. So one of these probes that was landing on a celestial body, its mission was very finite. So it only needed to function for what, like maybe an hour. So at that point, you can have a power source that is finite in scope. So primary batteries are usually very reliable. So they just stuck a primary battery, which is also very mass efficient, on this probe, sent it down. It carried out its mission. The primary battery died, but that's okay because the mission was over. Okay, and then I got a question about introducing the CubeSats that we're using in class, the Artemis CubeSat kit, in size and functionality. So I will do that folding into the other slides of the lecture today. All right.